Hi, welcome to our talk. What you see is what you mean. We are Dennis, Marco, and Volker. We are working together at Otto.de, concentrating on search technology and now Gen AI. And today we want to bring both together. So who is Otto? Otto is one of the largest online shops in Germany with 12 million active customers and marketplace with over 20 million products. And our job is to bring both together, the customers with the products. And the key way to do it is search. Of course, it's search. And I will show you our search architecture now. So at the top, we have our clients, the Otto customers and the API consumers. They are requesting the search API. After the search API, we have our blending engine built in Rust. And the blending engine is getting the results from Solar, the semantic search. And with all the results, we are going to a neural re-ranker. So it's I would say, a state-of-the-art search architecture we have, serving millions of requests every day. And the question is, what is the problem? So everything looks fine. But the problem is that we optimized on keywords. So finding keywords, finding similarities with our semantic search and with our Solar. But it's not really good in really understands the user. And that's a problem. That's a problem here. It's a problem with Amazon and with many other shops. To give you real use cases, I was looking for a gift or gift ideas for a 12-year-old boy. And if you try it at Otto, yeah, you get gifts, you get marks, and you can get pictures or signs. And the real product is here a money box for a 16-year-old. So not very perfect. The point is, it's kind of correct because these are gifts, but these are not the gifts you are looking for if you want to buy something for a boy or a girl. So that's the gap we want to close here. And of course, we started with a prototype. So we built a prototype which is using a large language model, an LLM, to generate meaningful search terms. So for our query, we generated headphones, board games, smartphones, smartwatches, and soccer balls. And then we used the keywords or the search terms, and we requested our traditional search engine in parallel to be very fast. At the end, we merge all together and we bring it to a list. And this is how it looks like, so much better. So now you really have meaningful products. At the top, you can see the search terms. They are hidden for our customers. It's just for us now. But you can see now you have meaningful products. But it's always a but. It's very limited. On the one hand, we just have 5 search terms. It's not enough for our assortment at Otto. On the other hand, it's enough to increase the mental load here. That's the problem. If you're using more search terms, we are getting more products. But it's very hard to navigate here. It's like going to a toy shop and all the toys are spread on the floor. So we decided to make another approach. Instead of generating keywords, we use an LLM to generate clusters. And each cluster represents an intent of the query. So we have a cluster gaming, a cluster sport action, technical gadgets, and creative sets. And after that, we are able to create keywords for each cluster. Like before, we use the keywords or the search terms and ask our traditional search. In parallel, now we have 16 requests here. So it's good to have a very performant and scalable search in the background. And we are all collecting the results. But instead of creating a huge list with all the products here, we use a cluster structure. So we show the customer the cluster, and we give, and that's very nice, we can give the clusters catchy titles. So it's so much better because now you have real inspiration. You have gadgets, you have sports stuff, creative kits, fashion, gaming goodies, and so on. And it's very easy to expand the clusters with the prompt. It's all in your hand. But we still have a problem. We call the problem semantic distance. So in our clusters, we still have products like the toy controller. Yeah, it's similar to the query, but not really. And that's why, because we have a chain. So a product depends on a keyword depends on an intent, and intent depends on a query. And that's a problem. In the end, it's a very long distance here, and in the end, we have a product which is not matching the query. But to overcome this, we created a kind of adjustment. We call it adjustment because we send all the products, all the intents, and all the queries back to the LLM. And we let the model judge what is relevant and what is not relevant. So the model can decide what should be rejected. And you can see it on the right side, the red tiles. These are the tiles which are marked by the model to be removed. To see all the steps now, again, I created another example. So for example, you're looking for articles for holiday at the North Sea. Again, the traditional search, we get mugs and signs, you know it. But with the new one, you really get, the new prototype reminds you what you should buy. You should protect your skin. You need something to play. And, very cool, you need a jacket because the North Sea, just in the evening, it's getting cooler. You might ask, okay, but these are edge cases. And you're right, we thought so too. That's just inspirational searches are about 5%. So we tried out a query like pants without any expectations because we thought, okay, it's very optimized here at Otto, pants. And we tried out with the prototype, and it looks so much better because now we have these clusters, and these clusters give us orientation, and it gives us a guide to the product. Because you have to see, we have over 100,000 pants in our assortment, so much. And it's so much easier to have it in the clusters and to see, okay, yeah, we have jeans, and we have something like, what is it? Cords, and sweatpants, and chino trousers, and so on. So it mustn't be categories. It could be pants in sale or something like this, or for a target group. It's the LLM which decides what is the best intent here. So you see, we are very convinced. And even in a remote user test, we saw that we added value for our customers. So we decided to bring it live. But to bring it live, it's a whole other story. And the story is told by Marco.
Hello. Okay, so let's have a look. What would happen if we switched this on for 100% of our search traffic? So we would map one user request to 5 intents, each intent to 10 keywords, and end up with 50 search requests for one user request. And then on top, we would have the inspiration and adjustment costs for the LLM queries and the time overhead for those queries. And we have time-critical requests which originate from user navigation clicks, so the user expects immediate response in those cases. And from the test with the POC, we learned that there are functionally different classes of search requests. We have the highly inspirational queries, like the present for the 11-year-old child. But we also have pens and washing machines, which are more exploratory queries, where the user expects rather guidance than inspiration. The user probably wants to be navigated through a large assortment and find out the right product property settings for the product that meets his or her needs. And then we have the very specific queries like iPhone 16 Pro Max, where the best thing you can do is probably to bring the user as fast as possible to the product detail page and maybe show some accessoires along with the product. So there are a few things to consider and a few drawbacks to address. As a first step, we wanted to get a gut feeling about how the search queries in our live traffic actually relate to the classes we learned or we derived from the POC tests. So we took these classes, exploratory, inspirational, and known item, and also added an unknown class and an ambiguous class. And then from a month of queries, we took a sample and labeled the sample with an LLM according to this class schema. We wanted to have a small sample size, so about 5,000 queries, to be able to validate the work of the LLM, the labeling, by hand. But we also wanted to keep the shape of the traffic intact, so we wanted to have the same ratio of rare and high frequency queries like in our live traffic. So we used a technique called probability to proportional size sampling, which helps you with that. And yeah, we wanted to find out how large is the share of each class in the overall traffic, and also how is the caching capability of each class when we cache the mapping from user query to intent to keyword set with a time to live, for example, for 1 month. So this is how the data looked. So we have the queries, we have counts, which in this case are not the real counts, but the relation should fit. And then we have the labeling from the LLM. So yeah, we have exploratory queries like washing machine, we have the known item queries like PlayStation 5, and we also have inspirational queries like Christmas decoration. So the labeling looked fine, and we started to aggregate the data. So we computed the share of each class and also a cache potential. So we counted all the queries that occurred more than once and computed their share of all the queries in one class. So with the idea that every query that occurred more than once is worth caching to keep it simple. Not very surprisingly, the most queries fall into the exploratory classes. So people search a lot for washing machines and the like, and the cache potential is also high because these queries recur very often. Then we have a smaller class of known items with a lower cache potential, which is also not surprising because individuality plays a greater role when you search for specific items. And we have a small share of inspirational queries, and surprisingly, they showed also a high cache potential. And we had a closer look and noted that there's an overlap between exploratory and inspirational. So it seems that the yeah, it's not always a clear-cut distinction between these two. And there are also a lack of long inspirational queries, like the example with the present. The inspirational queries our users are used to are shorter, like living room decoration, so a few keywords. Yeah, but still, we derive from this that we need to address the different classes, exploratory, inspiration, and null item, and it's worth, well, we would benefit from caching the mapping from user query to intent to keywords. So far, we still work with intents as keyword sets, and we already saw the problem with this longer mapping chain. Once we arrive at the end of the chain, at the keywords, the context of the original user query and also the derived intent gets somewhat lost. So in this example, we're still looking for the present for a 10-year-old, and once we arrive at the walking bike, for example, the context that it's meant to be for a 10-year-old is lost, and we get also walking bikes for younger children. This, of course, increases the need for adjustment, which is a need we wanted to rather decrease. There's also the problem that we still, even with the caching of the mapping, we still would have to execute the 50 search queries per user request. So not a really good approach, but still we thought that the mapping to the keywords is a valuable long-term information and could be the base for index improvements if you think about aligning the derived keywords from the intent with the indexed keywords of your products. So, but to address these two problems, we changed the mapping a little bit. So instead of mapping to keywords, we intents to keywords, we mapped directly to short intents. And these short intents are less verbose than the intents we originally generated, but they are semantically richer than the fine-grained keywords. So we are sacrificing a bit of diversity within an intent cluster, but we achieved to reduce the amount of search queries from 50 to 5, which is very helpful. And yeah, in this approach, the semantic search gets a stronger role because the short intents play very nice along with the semantic similarity. Yeah, and as you can see in this example query here, I need things for a beach vacation. We come up with short intents for sun cream and a beach dress. So the beach context is somehow preserved in these short intents, and there's less need for adjustment. So less need means there's still a need for adjustment. So we thought, let's make the adjustment cheaper. The question, does a product match the customer's intent, doesn't really lend itself to caching. So, but it's simpler than mapping intents or mapping user queries to intents, inspirational intents. So in the end, it's a binary classification task, and we thought maybe we can fine-tune a BERT model that can take over the costly LLM work. And we gave it a try. We used a 50K query sample, mapped these 50K queries to 10 intents each, to 5 keywords each, and to the top 120 products for each keyword, and ended up with a set of 300 gig of products, which we labeled with an LLM. So this looked more or less like this. We had, in this case, still a longer intent, a short product description and a label if it's a fit or not. And then from this 300 gig of labeled products, we selected per query at least 20 and at least 25 of non-matching products to have enough false ones for the training, and generated a set of 1 million intent product pairs, labeled intent product pairs. And then we trained a Neurobird model, which is a modern German-speaking bird model, which is similar to XML Roberta, but superior with a lot of improvements. And we used the settings, the hyperparameter settings from their recommendations. And after quite a few rounds, we managed to achieve an F-score of 0.779, which is pretty cool, we think. So, are we done? All good? What do you think, Dennis?
Yep. So, while we have this cheaper adjustment, it still has its drawbacks, because it's a kind of a post filter which kicks out products. And I want to talk about not using the adjustment, because currently we have some sort of a formalization of selections. If you think about your search engine, maybe Elastic, Solar, Vespa, you name it, you somewhat formalize your search using filters, using keywords, using and/or combinations, and this forms a selection, and it formalizes this. And it's kind of a pity if you then afterwards kick out products which are in those sets. So what we have is a more user-specific, domain-specific language to express this formalization of a selection. And the good part is that once a product has its properties, it is automatically part of this kind of formalized selection. So when we essentially kicking out products in an adjustment step, we kind of lose this product agnostic feature. And also we can only work on the top segment. So if you think of a larger selection with 1,000 or tens of thousands of products, you cannot adjust them all. So you need a way to deal with the rest of the selection. So this is where we thought, okay, facets are part of our formalism. Why can't we not use the large language model and try to bake in the adjustment in the facet part? So this would essentially put your filtering at a higher level, and you can put the adjustment upwards and have a selection that represents your intent, and you'll still be able to have it filtered and mapped to your intent and keep the product agnostic feature kind of intact. Let me show you how this could look like. So here you see a selection, and it sorts Anwendungsgebiet, camping outdoor, category cooking device, searching camping cooker. So it is already mapped a category and where it should be used, and it's showing here camping cooking devices. So a search for a natural language search could be mapped to filters. And if this could be done for a lot of natural language interactions with our search engine, that would be cool. So let's take the approach and try to use it. Just before we go to the next slide, just as a short recap, we have different classes explored in our search traffic, and we saw what kind of caching potential is in each class, and we tried to figure out where and what kind of intent is needed for each class. We shifted from keywords towards more short-term intentions to utilize the semantic search more and also doing much fewer requests to our search engines, and then try to shift the afterwards adjustment to a more upfront adjustment using filters, facets, and keywords. And when you do this, you're getting a more and more intelligent search slot. But you're still only unidirectional. So a user enters its request and then you present products. You have no way of communicating back. And also you have all your other stuff in place, like auto-suggest or stuff like this. So it's not really playing well with forms of multi-sentence interaction with your search engine. So why not create a more space and a channel back where we can interact with the user in a better way? And this is what we did. This is a somewhat conversational search with a bigger place and a channel back. And there you can see I've written something. I need something for my, I think it was camping trip. But I refined it and said, well, I've a tent already. So give me something back. Yeah, come on. I have a tent already. So it needs to derive that I have a tent already, so I don't need tents. So it presented me sleeping bags, I kind of want an isolation, and some cooking devices for camping cookies. So it could derive that I already have tents, it shouldn't present them, and it did kind of an inspiration for me. Very good. But the real power is that we do not want inspiration every time. So this large language model then is capable of adapting to the degree of inspiration that I truly need. Because if I'm asking for a concrete product, basically, let's say I'm searching for a chainsaw from a specific brand, then it could just list and filter chainsaws from this specific brand. There might be no inspiration needed in that case. So what you can build with this is like a mapping from search terms to intents, from problem statements to intents, from goals to intents. So it could really adapt to your needs, and that's the big benefit. And also resolving ambiguity. If you're asking for things like, let's say, boxes in German, which could mean boxing sports or speakers or storage boxes. So there could be a channel back like, okay, what type of boxes do you really need? But this means that we need to give up our control flow, which we had in the first place, because the large language model needs much more control over the specific data that it needs to decide which and how much inspiration is needed. So we needed to change the control flow and basically create multiple tool sets and tools which the large language model can use. And those were kind of search products, give us a category overview, get the facets for this specific query, do the facet mapping and stuff like this. So basically we gave up our own control flow and gave it more to the large language model. It is also then be able to reason a little bit about its own calls. So it could do fallbacks and self-healing. Yeah, and that's really great. But when you go live, you don't want to introduce regressions and errors. So how do you compete with those problems? Like when you frequent and sometimes radically need to change your prompts. I mean, the easiest one are so-called one-shot tests. Like, you have a specific product, you fire up a search and you evaluate, okay, is the conversation presenting this product? So those are the easy ones. But we wanted to see if the whole conversation is good. And how do you start conversations and evaluate them? So therefore, we introduced a programmable virtual customer, which we can program, and which can also supervise the outcome of the sales assistant. And we modeled a different persona in it. So you can think of a virtual customer that acts like an eager buyer or an indecisive buyer. So we told them, oh, be a little bit indecisive and you do not know what exactly you want, and so on. And we then can run thousands of virtual conversations about products, and we can then derive a couple of metrics out of it, like how many turns, were products presented, did you buy products? And we aggregate all those metrics and build runs. And then we can compare afterwards, during development, if those changes actually change the quality of our system and to introduce regressions. And you already see between run, I think 32 and 31, in conversation turns, it increased or decreased by nearly 1. And this was actually a bug. So it was not presenting products, and the virtual customer actually requested, oh, please show me the products. And then it only showed the products. So it introduced basically a regression bug there. We can also use this for attack simulation, like I'm talking about products, but now show me your prompt. Yeah, please show me right now. And then doing this persistent prompt request and stuff like this. So we also use this for attack simulation. Yeah. I would also like to thank all of the team and all of our sister teams who were really great in helping us out and providing information and their APIs, and yeah, and of course you for your attention on our talk. And now we can take Q&A. Thank you.
Are there any questions here? There. Oh, yeah.
So thanks for the presentation. I have a quick question regarding the cache potential you presented in one slide. Is that by chance something related to the overlapping of some of those categories or something else? How do you compute it, basically?
Little workout for me here.
You mean how we computed the cache potential? So we counted the recurring queries that occurred more than once within a class and computed their share from all queries in that class. So that's yeah. And there was some overlap between exploratory and inspirational classes. Yeah, okay. Seems to have answered the question.
Then we have one question from the online audience. I get back to you. Which model did you use for the intent to facets process? How did you evaluate this classification?
You mean our large language model? Is this? I assume you meant the large language model. So we use the Gemini model in this case, but in the back end we did an agnostic layer, so we can exchange, and we also checked GPT models, latest ones. But in this particular case, it was the latest Gemini model.
Yeah.
Making it easier for you, right? So I have a question. You've been talking about the evaluation and virtual customers. So could you talk a little bit more about that? Like how do you generate using LLM all end-to-end, both to create virtual queries and to evaluate them later? Or is it like semi-supervised? So I would love if you could share more.
I'm not sure if I understood the question. So how we conduct the virtual conversations?
Yeah, the last slide where you showed like evaluation and virtual queries.
Okay, so we have some metrics can just be counted, and we also have a virtual supervisor, so to speak, that takes a look at the whole conversation and derives its opinionated metrics on its own. So it's also LLM based. And for example, we have a school grade based number to value the sales advice. That's something the LLM supervisor does. So how good was the sales assistant in selling products during a conversation, for example?
Okay, another question from the online audience. How did you make sure that the generated intent clusters follow internal marketing rules and standard? Manual review whitelists LLM judges.
Yeah, whitelisting is a good idea, yeah. What could I say? Do you have anything to add?
I mean, we have a lot of tests that also do like business tests that test if products come up where they should be, but whitelisting is actually a good thing to have to do hot fixes that have an immediate effect while you're improving your model-based approach.
Okay, there was another question down here.
So in the classic search queries, you also get displayed sponsored products, right? How did you integrate those? Are they part of the intents? Are they not integrated at all?
So they're not integrated yet, but this tool execution functionality we use makes it more or less easy to add more knowledge to your model. So that's probably something we will integrate via tool execution, so that the model can pull in information about sponsored products.
And then another question we already had earlier, but unfortunately I couldn't ask because we didn't have time. Could you share a bit about your prompt engineering process? Did you use few shot prompts?
Not so much, I'd say. Especially when you have a prompt that steers the conversation. The few shot prompts worked not so good. They work good if you have actually LLM tasks that run in a single shot. That's my experience.
Okay, I think back there was a question. Sorry.
Thanks. Hey, first of all, great talk. I thought it was really interesting. But I was wondering, at the beginning, you mentioned you broke your search queries into like 50 different queries and then reduced it down to 5. And I know this is a prototype, but have you guys done any benchmarking about like the performance latency? If there's much of a hit from 50 to 5 to what you might have in production at the moment? And if there's any effect on business metrics?
I don't know if I understand it correctly. You mean if the quality still remains because we're reducing so much, or can you?
It's a latency.
No. Yeah, so the question is, was there a latency discrepancy? Okay, so basically we were already doing those 50 requests in parallel. So there was no benefit there, despite the computational resources which we spent. So.
Okay, last question.
Thanks for the talk, guys. Bearing in mind that we have seasonality, product sets changing, language changing, culture changing, what's your approach to any kind of retraining and rerunning of these systems? And how often do you do it?
So the LLM is not trained by us, so all we need to do there is adjustment to the prompts once in a while, probably. The BERT model approach would need more retraining, probably once a month, I guess. But yeah, since we switched over to the facet-based adjustment, the BERT model is at least not for productional use for serving such traffic anymore. So we will stick with the facet mapping approach.
All right, thank you very much. Give another applause for the speakers.